All right, so I want to preface this by saying that I'm going to try to go through this material rather quickly because this mini lab takes an exorbitantly long time to get set up. Once you have everything set up correctly, the experiment literally takes 3 to 5 minutes tops. Getting things set up can sometimes take you guys like an hour. Yeah, not shouldn't take you an hour in my jackass opinion, but it does take some of you an hour. So anyway, that being said, if you have any questions about any of this stuff, by means, obviously ask and I will be happy to answer them. So this is going to be our second and final lecture on op-amp circuits. And I'm going to call this practical op-amp topologies. So when we met on Wednesday, we discussed how to analyze an op-amp circuit, which is great because this class is about analysis. What we're going to be talking about today is how to actually use an op-amp to do things, which is a much more practical look at things, right? An op-amp is a tool used by circuit designers to perform mathematical operations on analog signals. So what I mean by an analog signal is one that potentially varies in time. Or actually, that's not really what I mean by an analog signal. By an analog signal, I mean one that is measured continuously in time, but op-amps are traditionally used for non-DC circuit signal processing, right? So just because all of the analysis that we happened to do on Wednesday was pertaining to how they would behave connected to a DC circuit, that's not really what they're used for. I was just trying to show you the rules of how these things work. All right, so the first circuit that we are going to look at is the most common configuration for an op-amp in practice. And it's actually something that we have seen to some extent. Okay. So I have my op-amp circuit. I'm going to ground my non-inverting input terminal, connect my negative feedback loop with some resistance here. I'm going to call this resistance RF. So that stands for feedback resistance. I'm going to measure my output voltage here. And I'm going to put some resistor here, which I'm going to call just R1. And I'm going to apply my input voltage at that left-hand leg of resistor R1 like so. So we're looking at things generically here. We're not necessarily trying to find a numerical value for anything. In fact, we can't because I haven't given you any numbers. What we're looking to do is figure out what the relationship between the output voltage and the input voltage is for this particular circuit. So if we apply step number 1 of our analysis procedure, we would see that these two currents are 0 amps and 0 amps respectively. Step number 2, we would observe that the voltage present at our non-inverting input terminal is 0 volts. Step number 3 tells us then that the voltage present at our inverting input terminal is also 0 volts. Applying Kirchhoff's current law at our inverting input node will give us the relationship negative Vn divided by R1 minus V out divided by R2 is equal to 0. So I just got rid of the 0 minus parts of those expressions because they don't really do anything for me. And now I'm going to do simple algebra here. And in doing so, I could find that the output voltage of this op-amp circuit, V out, is equal to, sorry, I put R2 and I meant to put RF, my apologies. negative RF divided by R1 times Vn. So anytime we see this topology, it will have this voltage relationship, right? Once again, it does not matter if we choose to put some resistance here between ground and our non-inverting input terminal, or if we choose to use this circuit to drive some load resistance. That doesn't matter at all. This equation is the characteristic equation that governs how this particular circuit works. Okay? I'm going to introduce a new term to you all right here. Excuse me. AV. So A is the symbol that is traditionally used for gain in an amplifier system. And the subscript V specifically means that we are looking at a voltage gain. So the voltage gain of this system is nothing more than the ratio of V out to V in. And for this particular circuit, our voltage gain is negative RF over the resistance R1. So the gain of this system is described entirely by the ratio of the resistors that are used to bias this circuit. This is one of the principal advantages of negative feedback systems, is that usually our system gain will depend only on what we bias it with and not the internal gain of the op amp itself, which, by the way, happens to usually be on the order of several 100,000. This allows us to control the gain and set it to some specific value. Okay. So, excuse me, don't know what's going on with my throat today. So let's talk about this gain relationship here briefly, okay? So the gain of this system is negative RF over R1. There is no real restriction on what RF and R1 can be, other than if we chose R1 to be a short circuit, it looks like we would have an infinite amount of gain. And in circuits 2, we'll talk about the consequence of that, but won't be that big of a deal for this class. So because RF is unrestricted and R1 is unrestricted, this particular type of amplifier is capable of amplification, so making our input signal larger, which would happen when RF is greater than R1. And it's also capable of providing attenuation, meaning making our output signal smaller than our input signal, which would occur if RF is smaller than R1. So we get two different kind of operational modes here, right? This particular circuit is used to make signals either larger or smaller. And the quote unquote downside to this increased functionality is that it also inverts our signal. What I mean by that specifically is we can see that our voltage gain here is a negative quantity. So if we put a positive voltage in, we get a negative voltage out, and vice versa. So for this reason, this particular circuit is called an inverting amplifier. So on the theory part of your exam, those first 5 questions, something I might ask you about a circuit like this would be, what could we do to increase the voltage gain or the magnitude of the voltage gain of this system, right? So what changes could we make to this circuit that would result in AV being a larger quantity in magnitude? So as RF goes up, the voltage gain goes up. What's the other thing we could do? Decrease R1. So as R1 goes down, the voltage gain also increases. Absolutely. So that's the kind of theory type questions you should expect for these type of circuits here, okay? All right. So before we move on to our next circuit, does anybody have any questions about this one? Well, so changing the voltage does not necessarily change the gain because the gain is the ratio of the output to the input, right? So if your input voltage is smaller, your output voltage will also be smaller by a factor of the gain, which means that ratio actually stays constant. So the only way to change the gain is to change the bias circuitry, in this case, the resistors of the amplifier. Any other questions about this one? All right. So for our next circuit, by the way, this is one of the two circuits you're going to be making today in your lab. For our next circuit, we are literally going to change two things. So it's going to be this circuit almost identically, except for very slight change. Give myself a little bit more room this time. So I've still got my feedback resistance R sub F. Connecting my inverting input terminal to my output terminal. I'm going to measure my output voltage directly at my output terminal. I'm still going to have this resistor R1 here. The change that I am going to make is that I'm going to swap the positions of ground and where I apply my input voltage. So this circuit is literally the exact same thing as our previous circuit, except that the position of these two things is switched. That is a very strong hint as to how you should switch between these two circuits when you're doing your lab, because this is the other circuit you're going to be making. Okay? They are literally identical, except the location of where we apply ground and where we apply our input voltage have been transposed. So let's analyze this thing and figure out what our input-output relationship for this particular amplifier is going to look like. So applying step one, which is rule number one, we know that both of these currents must be zero. We can see by observation that the voltage present at the non-inverting input terminal is simply Vin, which means the voltage present at the inverting input terminal is also Vn. Applying Kirchhoff's current law at our inverting input node gives us the relationship Vn divided by R1 plus Vn minus Vout divided by Rf is equal to 0. Excuse me. And doing a small amount of algebra gives us the relationship Vout is equal to 1 plus Rf over R1 times Vn. And we can easily see then that our voltage gain, AV, always defined to be the ratio of the output voltage to the input voltage, is just 1 plus Rf over R1. So let's talk a little bit about this guy. So our previous amplifier was capable of achieving both amplification, making our output signal larger than our input signal, and attenuation, which is making our output signal smaller than our input signal. This amplifier is incapable of attenuation because even if RF were 0, short circuit, and R1 were infinity, an open circuit, the smallest our gain could ever be would be 1. Just as a heads up, if we were to replace RF with a wire and R1 with an open circuit, we would have what's called a unity gain buffer amplifier. That's just a special case of this type of amplifier, where a unity gain buffer is used to copy an input signal, but allow it to effectively produce more current, right? So some sensors are incapable, or they can produce a reasonable amount of voltage, but they can't produce a lot of current. So if you think, how many of you guys know what a piezoelectric crystal is? One person. How many of you guys, actually, how many of your parents have a gas grill that has a push button ignition? Exactly right. So that is a piezoelectric spark generator. So effectively, when that crystal mechanically deforms, it creates a large voltage. Yeah. However, just because it's capable of creating a large voltage, enough to literally cause arcing and light a grill on fire, does not mean it can produce a particularly large amount of current. Actually, the current produced is extremely small. So if you had a piezoelectric sensor that you were using to, say, measure vibrations or something like that, because you're just going to be measuring some sort of mechanical deformation of this thing, you would need to run the output of that sensor through a unity gain buffer in order to allow the power supply to add current to your system so that you could use that sensor's output to actually drive some sort of load. So unity gain buffers, even though it literally just has a gain of 1, is a fundamentally necessary op amp application. All right. So as I said a moment ago, the minimum gain that we can get for a system like this is 1. The maximum gain is however large we can make RF compared to RN. So we're always going to have amplification with this system. And we also do not have inverting here, right? So 1 plus RF over R1 for positive resistor values, which is what we're going to be able to connect to this thing, will always yield a positive voltage gain. So this particular amplifier is what's known as a non-inverting amplifier. So before we move on to our next circuit, I want to look at these two at the exact same time to kind of show you a very easy way to figure out which type of amplifier you have because they are so incredibly similar. If your input signal is applied on the non-inverting side of the amplifier, you have a non-inverting amplifier. If the input voltage is applied on the inverting side of the amplifier, you have an inverting amplifier. That is all it takes to differentiate between these two things. All right, so any questions about inverting or non-inverting amplifiers to this point? All right. So the next circuit that we are going to look at is a modified version of the inverting amplifier. So for our inverting amplifier topology, our non-inverting input terminal was connected to ground. We had some feedback resistance RF connecting our inverting input terminal to our output terminal like so. And then we measured V out here directly at the output terminal of the op amp. The changes that we're going to see are over here on the left-hand side as to what's connected to our inverting input terminal. So if we had a single resistor here, let's call it R1, let's call this voltage V1, we would have just our basic inverting amplifier topology. If I connect another resistor, let's call it R2, and apply an input voltage V2, and let's say a third, I could actually do an infinite number of these. Let's just stop at 3. R3 and V3, we now have effectively an inverting amplifier that has 3 inputs, okay? So let's apply our rules and see what the ratio between, or the relationship between the output voltage and these three input voltages are. So we know that our currents flowing into the input terminals must be 0 amps. We can see by inspection that V plus is equal to 0 volts, which means V minus is equal to 0 volts. Applying Kirchhoff's current law at our non-inverting input node, what we are going to get is negative V1 divided by R1 minus V2 divided by R2 minus V3 divided by R3 minus V out divided by RF is equal to 0. And rearranging this, we find that V out is equal to negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. Again, if we had more inputs, we could continue this progression. So let's look at what our output signal is here, okay? So if we were to distribute that factor of RF throughout each of those things, we would effectively see that our output voltage is just a combination of scaled versions of each of our three inputs, and those scaled versions are just added together, okay? So this amplifier is what's known as a weighted inverting summer. Let me write that down. So it's weighted because each of the input signals has a specific weight applied to it, established by the gain of that portion, right? So the weight of the input voltage V1 is defined by the ratio of RF over R1. The weight applied to input signal V2 is defined by RF over R2, et cetera, et cetera, et cetera. So we can scale different signals by different amounts and then add all those results together using this type of amplifier. Now, what if R1, R2, and R3 all had the exact same value? So let's put that down here. So if R1 is equal to R2 is equal to R3, our output voltage relationship, V out, would be negative RF over R1 times V1 plus V2 plus V3. This is just an inverting summer. All of the different input signals have the exact same weight applied to them. Okay. So where do you think something like an inverting summer might be used? How many of you guys own a digital bathroom scale? Or your parents own a digital bathroom scale? Okay. A few of you. How many of you have any idea of how a digital bathroom scale works? Probably none of you, okay? Let me illuminate you here. So if we had a bathroom scale, and by the way, this is actually the exact same way that a weigh station at a truck stop works. Yeah. So this is our scale, right? And then we have probably a metal strip or something like that here, and a metal strip or something like that here, telling us where we should put our feet, right? Well, there is usually some form of nickel strain gauge where the heel of your foot and the ball of your foot are going to make contact on this scale, okay? How many of you mechanical engineers know what a nickel strain gauge does? So a nickel strain gauge uses a property called the piezo resistance of a material in order to cause a change in an output voltage. So piezo resistance is the change in resistance due to mechanical deformation. So when you stand on these nickel strain gauges, they deform, causing a slight change in their resistance. And so if you apply a bias voltage across that nickel strain gauge, you're going to see that the voltage moves away from its equilibrium point when you deform this thing. An inverting summer would then be used to amplify all of those deflections and add them together to give you an overall idea of what the weight or the strain on the system is. So this is literally a direct application of an inverting summing amplifier, is common commercial product like a digital bathroom scale. Takes all of those different strains, amplifies them by some factor that corresponds to your weight. So you could think of the output of the strain gauge as being probably millivolts per pound. Add those millivolts per pound together, scale it by the appropriate scaling factor established by the resistors to make the math work out, and boom, your weight is shown up as the digital output. Probably it's going to be a different compound that would be used. So the nickel strain gauges are very sensitive. Nickel has a very high, I'm trying to remember what G is. So E is Young's modulus of elasticity. What's capital G in mechanical engineering? No. Might be the rigidity thing. And so there's a relationship between E and G called Poisson's ratio. Am I mistaken there? So nickel has a very high Poisson's ratio, meaning that it's easy to deform. And that's why it's used in conventional, like that's why it's one of the most useful things in piezo-resistive sensing. So I think you might still be able to use a nickel strain gauge, but it probably won't be as rigid as what you would use in a bathroom scale, or definitely not at a weigh station measuring the load in the back of a truck or something like that, because you don't want it to completely, yeah.
So the resistance is based on the shape of the metal?
Right.
So when it's mechanically deformed, it's the
resistance. Yep, that is piezo resistivity in a nutshell. All right, so to this point, let's review what we've talked about, okay? We've talked about how to make signals larger and smaller if we're okay with having an inverted signal. We've talked about how to boost signal power effectively with a unity gain buffer, or just make the voltage larger with a non-inverting amplifier. Now we have seen how the mathematical operation of addition is carried out using op amps. So let's now talk about subtraction. So what we're going to be talking about here is a differencing amplifier. And the differencing amplifier is really just an inverting amplifier and a non-inverting amplifier at the same time. So we're going to apply an input signal to both our inverting input terminal and our non-inverting input terminal. So I'm going to start with the bias network applied to my non-inverting terminal. So I'm going to have some resistor R here. Some identical resistance R here. And I'm going to call this voltage V2. I have my feedback resistance, which is also going to be just R. Here's where my output voltage is measured. And then I'm going to have a fourth resistance R, where all of these resistors are matched to have the same value. And this is going to be my input signal V1. So analyzing this guy, we have 0 amps here, 0 amps here. What is the voltage present at my non-inverting input terminal going to be? What? I disagree. V2 over 2. Why is that, Ethan? Exactly right. So we are effectively biasing the non-inverting input terminal with a simple voltage divider circuit here, right? So recall this voltage V plus is a nodal voltage. It's measured with respect to ground. That is the exact same thing as the voltage drop across this resistor R that is in this vertical position, right? We know that no current can branch off and flow into the input terminal. So any current supplied by our source V2 is going to wind up flowing through this resistor R and then flowing through this resistor R on its path to ground. So from the perspective of our voltage source V2, all we see is two identical resistors in series, and we're just looking for the voltage drop across one of those resistors, which is exactly going to be V2 divided by 2. For our next step, we would know that V minus, the voltage at the the inverting input terminal, is the same as the voltage at the non-inverting input terminal. So this voltage here is also, sorry, V2 over 2. Applying Kirchhoff's current law at our inverting input node, we are going to have V2 divided by 2 minus V1 divided by R plus V2 divided by 2 minus V out divided by R is equal to 0. I'm now going to multiply both sides through by a factor of R to just get rid of those guys. 0 times R is still just 0. And I'm going to add things together. And what we're going to find is that V out is simply V2 minus V1. So this is a differencing amplifier because the output of this amplifier is simply the difference between the two input signals, right? We're famous for those. All right. So any questions about the differencing amplifier here? Anytime we want the difference between two signals. So it would be, I mean, that sounds flippant, but that's literally what it's used for. Literally any application where we want to know the difference between two signals. It would be part of radios and things like that in order to get rid of carrier signals. So typically you have a message signal on top of a carrier signal. If you subtract the carrier signal out, then all you're left with would be a message signal. Yeah. All right, so we've done addition and subtraction. Unfortunately, we cannot do multiplication or division with a single op amp, but we can do integration and differentiation. So now we're going to talk about how op amps do calculus. Okay. Nope. Nope. It's not nearly as bad as you guys think. Would you rather the rock do it or you do it?
Yeah, several that can go with pretty rocks into thinking and sit down those.
All right, so both the integrating amplifier and the differentiating amplifier are really just special cases of a non-inverting amplifier. But instead of using strictly resistors, we are going to use an energy storage element. Now, I am going to derive these relationships using capacitors specifically, but we could just as easily implement these types of amplifiers using inductors as well. Okay. So I'm going to start with this one here. I'm going to put a capacitor in my feedback loop. Here is my output voltage, and I'm going to explicitly mention that this is a voltage that's varying in time. I'm going to ground my non-inverting input terminal, and I'm going to place a resistor between my input signal Vn as a function of time and my non-inverting input terminal. So before we figure out how this thing works, we need to refresh ourselves on what the relationships are between voltage and current in a capacitor, right? So we know that the current flowing through a capacitor is C times the derivative of the capacitor voltage with respect to time. And we know that V can be written as 1 over C times the integral from negative infinity to T of the capacitor current with respect to time. I'm using the integral from negative infinity to T just to make the math easier here so that we don't have to worry about the impacts of the initial condition on the capacitor voltage, just as a heads up here. Okay. So I am going to define my capacitor voltage as this voltage, positive polarity on the left. And I'm going to define my capacitor current as the current flowing into the positive polarity terminal of my capacitor. Okay. And we are effectively going to do the exact same steps that we have done previously, but because we have these energy storage elements in here, we're going to have to think about it a little bit more to understand what the relationship is. Okay. So let's start by observing that no current can flow into or out of our input terminals. The voltage present at the non-inverting input terminal is 0 volts, which means the voltage present at the inverting input terminal must also be 0 volts. And what I'm going to do now is I'm still going to do Kirchhoff's current law, but I'm going to do it slightly differently. Okay. So I'm going to say that the current flowing in has to equal the current flowing out. Okay. So that tells me that Vn as a function of time minus 0 divided by R is equal to IC of T. Now, our goal here is to get a relationship between the output voltage of our amplifier and the input voltage applied to our amplifier. We have something with respect to IC of t, so how can we relate either of those quantities to VC of t? Because we know that there are relationships between IC and VC, right? So what would the relationship between VC of t and V out of t be for this particular circuit? So what's the nodal voltage at the positive polarity terminal of VC of t? 0, okay? So we're going to have VC of t is equal to 0 because the nodal voltage at this node is 0. What's the nodal voltage at the negative polarity terminal of VC of t? V out. So VC is simply negative V out. And now I'm going to use that relationship and our relationship for capacitor voltage being effectively the integral of capacitor current. And what I'll find is that V out as a function of time is going to be negative 1 over C times the integral from negative infinity to t of IC of t prime dt prime. Substituting in my relationship for IC of t, I will have Vn of t divided by R, Vn of t prime divided by R, excuse me, dt prime. And finally, since my resistance value is a constant, I will just have negative 1 over RC times the integral from negative infinity to t of my input voltage with respect to time. So this particular configuration, I'll scroll back down there in a moment, is what's called an integrating amplifier. And the integrating amplifier is a very interesting amplifier because not only is it used to perform the mathematical operation of integration for analog signal processing, but it is also a fundamental building block of both control systems and communication systems. So in a control system, this is a part of what's called a PID controller, a proportional integral differential controller. In a communication system, this is an active filter. This would be an active high pass filter, meaning that low frequency signals would be rejected by this system, whereas high frequency signals would pass through, scaled by a factor of negative 1 over RC. And we'll talk about that frequency dependence of things a whole heck of a lot more once we get into steady state sinusoidal circuit analysis, which is our next big topic, where we're going to be looking at circuits in what I'm going to call the frequency domain, okay? So this is a fundamental building block of like 3 or 4 different aspects of electrical engineering, okay? So just as a heads up kind of thing, I derived this using a capacitor. If we were going to derive this using an inductor, we would actually have to switch the locations of R and the inductor in order to get this output relationship, okay? The last circuit that I want to look at, actually, let me make sure, does anybody have any questions about any of this guy's stuff? Okay. So the last circuit that we're going to look at is literally the exact same thing that we just had, except that we're going to swap the position of R and C. So my resistor is going to be in the feedback position. Here is my output voltage. Here's my capacitance. Here's my input signal. Once again, IC is C dV by dt. VC is 1 over C times the integral from negative infinity to T of IC T prime dt prime. I'm going to define my capacitor voltage with positive polarity on the left and define my capacitor current as flowing in to the positive polarity terminal. Now I'm going to do my analysis. So we know that this current is 0 amps. This current is 0 amps. The voltage present at the non-inverting input terminal is 0 volts, which means the voltage present at the inverting input terminal is also 0 volts. And once again, I'm going to apply Kirchhoff's current law as the current flowing in to the inverting input node is equal to the current flowing out of the inverting input node, giving me the relationship IC of T is equal to negative V out divided by R. So for this particular circuit, now I need to figure out how VC of T is related to Vn. So what is the nodal voltage at the positive polarity terminal of VC? Vn. What's the nodal voltage at the negative polarity terminal? 0. So in this case, VC is just directly Vn of T. Okay. So IC of T is C dVc by dt, or C dVn by dt, and we know this is equal to negative V out over R. Rearranging, we find that V out is negative RC times the derivative of our input voltage with respect to time. So this is a differentiating amplifier from the perspective of analog signal processing. It is also an integral part of a PID controller. It provides the D. And it is also a low pass filter in communication systems. So these are the most widely used negative feedback op-amp circuits out in industry. For those of you that are in mechanical engineering, biomedical engineering, and certainly electrical engineering, if your senior design projects have literally any type of electrical component, I'd be willing to bet part of it is going to be one of these 6 amplifiers. So, just as a heads up. All right, so that's all that I wanted to talk about for today. There is no in-class assignment. The remainder of the class is dedicated only to getting the lab finished. So if you have any questions about that good stuff, please let me know.